So we can move to the next paper. It's presented in person by Francois.
All right, great. Can you hear me? Yeah, awesome. Hi, everyone. I'm Francois Mérez from Amazon Music, and I'll be presenting some recent work on conversational recommendation for Alexa. And this is joint work with Songhao Luo and Tao Ye all at Amazon Music. Okay, so at Amazon Music, one of our goals is to essentially, when a user asks Alexa to say, hey, play some music, we want to be able to play the right content right away all the time. However, sometimes we're missing some information to do that. So we were wondering, like, what if we start asking some question to the user? Can we improve the overall recommendation quality? So we launched our first conversational experience about 2 years ago. Essentially, users can say, Alexa, help me find music. And then Alexa starts asking some questions, like about the mood of the user, for example. Then the user can specify some constraint, like, oh, I would like 90s rock. Then Alexa can decide to choose a specific entity and play an audio sample to the user. And it sounds like this.
No problem. Try this. Nirvana. Did you like it?
So then, like, if you're not into grunge music, like in the morning, you can just say you don't want that, and then provide other constraints, and Alexa can choose to ask more questions, and essentially the conversation ends when the user accepts the content that we recommended, like by starting a playlist, or the user abandons. So behind this experience, a key question is what questions should we ask and in what order? So there's a wide range of questions we can ask, like from very broad questions on the left to more specific questions on the right. And those questions have very different properties. For example, the ones on the left, they tend to impose a fairly high cognitive load on the user because the user has to figure out something on the spot. The questions on the right, they impose a much lower cognitive load because the user can just say yes or no, for example. On the other hand, the question on the right, they require very good personalization to get it right. So you can see it's far from trivial to decide on what question to ask. So we decided to model this as a reinforcement learning / bandit problem. And we want to learn a dialogue policy that tells us what Alexa should say next to maximize some measure of task success. And more specifically, instead of building some kind of user simulator, we want to learn from live log data. And so to summarize, we want to learn a target policy from data collected using a logging policy. And this is part of a larger offline policy optimization framework in which we start by collecting some randomized conversational data with live users. Then we make sure we log the state, the action probability, and the reward at every step of the conversation. And once we have collected data, we can use that to do offline policy optimization and evaluation counterfactually. Is we can try all sorts of parameters, exploration techniques, and by counterfactually, I mean we want to estimate the reward of the policy that we just trained, even though we only collected data using a logging policy. So once that allows us to pick a good candidate, we can deploy it to customers and do an A/B test, and we can confirm whether the new policy beats the old one. And if we want to improve the experience, we can, let's say, add a prompt. We can go back to collecting more randomized data and start again. So I'll focus a little bit on the counterfactual evaluation. We use importance sampling, also called inverse propensity scoring. And essentially, the idea is that we have a logged reward from the logging policy, and we can just reweight them using the probability of the target reaction according to the target policy divided by the action probability according to the logging policy. And with this reweighting, we get an unbiased estimator, which you've probably heard of, but it's unbiased, but has a fairly high variance. There's all sorts of tricks to reduce that variance. And in our work, we started using the sequential version of this estimator. So what should we optimize for? So in our experience, it would make sense to optimize for task success. That is, did the user end up playing something we recommended at the end of a conversation? However, for our first models, we decided to focus on something that's potentially less noisy, and we call that prompt usefulness. And so it's a slight tweak on task success. For a prompt to be successful, not only does the conversation needs to be successful, but also the prompt needs to yield to an answer from the user that's actually useful into finding the entity that gets played at the end. So for example, if we suggest 80s music and the user says yes, and you play 80s music at the end, then we get a usefulness of 1. Had we played like 70s music at the end, the usefulness of that prompt would have been 0. So in order to learn what to ask next, we need to define a feature representation for the state or the context. And we use features characterizing the information that the user provided within the conversation, the length of the conversation, the subscription tier of a user, and many more features. We also need a feature representation for every action. By action, I mean an actual prompt, a candidate prompt. And we represent the meaning representation of the prompt. For example, the type of slots being represented, like genre, era, or artists. We also have features for the type of question being asked, whether it's open-ended or a suggestion or something else. And also, we also have an embedding-based affinity feature that tells us the affinity between the user and the entity being suggested. I'll get back to that one later. So once we have our state representation and our prompt representation, the simplest kind of policies, we can build our reward regressors or value-based policies where you simply concatenate those two features and you're trying to learn a function that predicts the reward for every state and prompt pair. And once you've done that, you can use any kind of exploration scheme, or you can use a greedy action selection by picking the action with the largest reward. And what's nice about the offline policy evaluation framework is that you can try out all those types of model and exploration schemes and see which one, you can estimate the performance of each one of those. So we compared a few algorithms. So we compare offline linear models with Thompson sampling for exploration. We also evaluate neural bandits. We also tried an XGBoost regression tree with Boltzmann exploration. And recently, we just started looking at a policy-based method by looking at the offline policy gradient. So in our first offline experiment, we wanted to assess, can we do better in our rule-based system that was in production for like a year or so. So it was a fairly decent rule-based system, which has seen a lot of traffic. So we collected some data, and we did a regular cross-validation, and we were able to measure the predicted reward for all those models. And we found that XGBoost somehow surprisingly performed better than our rules by 12% relative in terms of prompt usefulness. So that was pretty encouraging. So we picked that model to deploy to customers. So then we wanted to check whether this actually makes a real impact with live users. So we did an A/B test, just comparing the rules with the XGBoost policy. And what we found is that we got an 18% lift in question and prompt usefulness, which kind of expected because that's the metric we optimize against. We also found an 8% lift in task success. And by task success, I mean the number of conversations that end with playback. Interestingly, we also noticed that for conversations that led to playback, those conversations ended up being like 20% shorter. So that was a great finding for us. It means the users got what they want more often, but also quicker. So in that first experiment, we only had one candidate prompt that presented a specific entity. So the model had to pick between, decide whether what question to pick or whether to recommend something. In the second experiment, we wanted to evaluate whether we could extend the set of candidate entities suggestions. And we want to learn not just when to recommend, but also what to recommend using a single model. So what we did is extending the set of candidates by adding multiple entities based on the search results of our search engine. And in order to be able to discriminate between those entities, we added a single embedding affinity feature between the user and the entity being suggested. And again, we did the same offline policy optimization and evaluation work to pick a model. with hyperparameter tuning. We deploy that to customers and did an A/B test to compare it to the previous model. And what we found is that with a single feature, we get a 4% lift in terms of the conversation that lead to playback. And you also found another 13% reduction in conversation length for successful conversations. So that was also a great result because it's only by adding a single action feature to a model. All right, so in terms of future work, so we want to investigate moving away from fully observable states to partially observable states. The idea is that we want the model to learn to learn from the dialogue history what to say next, and we also want to look at more fine-grained variation, like looking at natural language generation to control things like stylistic variation, and also, for example, whether we can recommend multiple items in a single utterance. And we also recently launched our first multimodal experience for our conversation. So an interesting area of work is to train a policy that lets you predict voice action, but also predict visual actions. OK, so beyond conversational AI, we'll have lots of other interesting projects at Amazon Music, like focusing just straight on music recommendation, like when user says, Alexa, play music, like what do we serve? We also have a great team focusing on language understanding to parse complex Alexa utterances, like those one. And finally, we also have a search team that focuses on finding the right entity given a complex set of user constraints. So if you're interested in any of those projects, feel free to email me. We're looking for machine learning scientists, software engineers, and we're looking in San Francisco. It's a very cool office. So please write me an email if you're interested. And thank you for listening, and open to answering questions.
So we actually have a question online from Andrea Barrazza. Could a simulator be built to simulate conversations to train offline reinforced learning policies with safer explorations that consider long-term rewards? For instance, a simulator might be useful to study approaches like Monte Carlo tree search.
Like what research?
Monte Carlo tree search.
Oh, I see. Yeah, I mean, we could definitely. I mean, we even have some data from users we could use to train a simulator. It's just that this was kind of like a last resort. I know there's lots of other efforts that involve simulation that makes it much easier to investigate more higher capacity models, because obviously data is a limitation. However, to us, it's not really clear that you can learn much more than what you put in that simulator. So we're trying to see how much we can go without any simulation. And that's kind of that's kind of right now, that's what we want to focus on. And the other challenge is that a simulator, it's just very hard to build a reusable simulator. And you could argue it's probably harder to build a good simulator than building a good dialogue policy in the first place. So yeah, I think it's possible, but it's not really something we're focusing on now.
Okay, thank you very much. Can you also comment, please, on kind of like any heuristics on how you generated the embeddings, kind of like what were the approaches that you used for them?
Oh, I see. Yes, so this work kind of assumes that there's a latent representation available to use, so we did not really, I know there's some other work that tries to create the embeddings based on the result of a conversation, but we are assuming the embeddings are there for users and items. So yeah, it was generated using the standard metric factorization methods, so we just assume that they're present in this work for now. Yeah.
Okay, I see. Thank you very much. There are a few more questions, but I guess we can take them offline, and for the sake of time, we proceed
Thank
to
you.
the next one. Thank you very much. So the next